Hello everyone. So in today's class we are going to discuss 11th PU Physics 11th chapter, that is Thermodynamics. So we will write which are the concepts we are going to discuss in today's class, and based on those topics we will solve some of the previous year questions which has appeared in JEE, NEET, CBSE as well as in NCERT session, and then we will move to some of the basic definitions related to thermodynamics, and then we will cover half of the unit in this video. So let us begin the session. So which are the things we are going to cover in this is, the first one is some basic definitions, and then thermal equilibrium. So what is mean by thermal equilibrium, and then zeroth law of thermodynamics, and first law of thermodynamics, and the first law of thermodynamics. So these are all the things we are going to cover in depth in this session. So what are the things here we can see is thermodynamics, right? So what is thermodynamics? If we split this thermodynamics means we will get the two phenomena. The first one is thermo and the second one is dynamics. So what is thermo? It means heat, and dynamics means which is in motion. So can we say that heat is in a motion, or can we define like this? No, right? So what is the definition of thermodynamics mean? It is a branch of physics which deals with the study of heat energy, temperature, and the interconversion of heat with the other forms of energies. So what this interconversion means? Heat energy can be converted into light energy, or heat energy can be converted into mechanical energy. So these are the interconversion that is going to take place in this mechanical energy. So heat is converted into light, or light is converted into heat energy, mechanical energy is converted into heat energy, or heat energy is converted into mechanical energy. So this interconversion is going to happen in thermodynamics. So one more question arises here, right? So is this a thermodynamics a microscopic study or a macroscopic study? So microscopic means which is in small, or we can say that which is of a tiny particle study, and macro means which is in large or in a bulk quantity study is called as macroscopic study, right? So thermodynamics is a macroscopic study. This thermodynamics is a macroscopic study. Why? Because here we are going to find in large quantity the pressure, volume as well as temperature of the thermodynamic systems in large quantity. So hence this is a macroscopic study. So microscopic study means which are the things involved in that? The proton, neutron, electron. So all these things are having certain mass, certain size, certain shape. So this is about a microscopic study. Hence we can conclude that thermodynamics is a macroscopic study. Next comes the system. So as we have discussed, this is a large number of particles. They are having a system is nothing but, if we consider this as a container, and this is it is having some of the molecules in it, right? So if this is a system and this system is having certain pressure, certain volume and certain temperature. So that system involves pressure, volume as well as temperature in a large quantity, or the particles here will be in large number. So that is nothing but a system. And then comes the surrounding. If we consider this as a system, and the things which are directly in contact with this system are called as surrounding. So what is surrounding? Everything outside the system which have a direct effect on the system. So if the pressure increases, then it will increase by the surrounding. If the pressure decreases, again it will decrease by the effect of the surrounding. So except the system, everything that is present and which is in direct contact with the system is called as surrounding. Okay, so next thing is we will discuss the types of systems. So what are the types of systems and how many are there? There are three types of system. The first one is open system, the second one is closed system, and the third one will be isolated system. So what happens in open system is the energy as well as matter, both of them will exchange here in open system. But what happens in closed system? Only the energy is exchanged but not the matter. What happens in isolated system? Neither the energy nor the matter is going to exchange with the system and the surrounding. If we consider a day-to-day life example or a general example, if we consider this as a cup of coffee. So this is a cup of coffee, and what happens over here is, if we supply a heat energy here, so if we supply some heat energy here, so here energy is exchanged, right? Here the energy is exchanged, and then if here the particles will directly come into contact with the surrounding. Hence we can say that matter is also exchanged with the surrounding. Hence if we consider this cup of coffee, both the energy as well as matter is exchanged. Again, if we consider it in a closed system, it is covered with the container. If the cup of coffee is again closed with the container and it is supplied a heat energy. If we supply a heat energy here, only the energy is exchanged but the particles will remain inside this cup only. Why? Because the matter is not going to exchange with the surroundings since the container is closed. Right? So this is about the closed system. And then comes the isolated system. For this, the best example is thermos. Neither the energy exchanges nor the matter has been exchanged with the surrounding. So next comes one of the concept is thermodynamic variables. So what are the variables do here? So which are those variables? The variables like pressure, volume, temperature, these things will tell the behavior of the system, like how the system is behaving, whether it is cool, whether it is hot, whether the internal energy is increasing, whether it is decreasing, or whether it is expanding. All these behaviors can be explained by these variables in the system. So hence it is called as thermodynamic variables. So if we check the definition, it says that quantities like pressure, volume as well as temperature, which describes the behavior of the system, is called as thermodynamic variable. So then comes the two types in thermodynamic variables. That is, the first one is path variable and the second one will be state variable. So what happens in path variable is, it depends only on the path but not on the initial and final positions. If we consider a state variable, here it depends on the initial as well as the final position. So if we check again our day-to-day life example only, here we are going to college to school or college to home. Here it depends on the path, like how you are going, whether you are taking a shortcut or whether you are going from a long route, or whether you will go to a temple first and then to the college and then to the home. So all these things, the path matters in path variable, whereas only the initial position as well as the final position matters in the state variable. Whether you are in college, whether the initial position is in college and the final position is in home. Only matters here is the initial and the final places, but not the path how you have taken, whether you have taken the long route, whether you have taken the short route. It won't matter in the state variable. Okay, so let's move to the types of state variables. Which are those types? The first one is extensive state variable and the second one will be intensive state variable. So what happens in extensive state variable is its changes can be seen by its size and shape. So the changes like volume, mass, these changes can be easily observed through our naked eyes, right? So whether we have taken a water in a container, whether we have taken a water in a cup, so here matters is volume. We can easily find out that this is in a large quantity, this is in a small quantity. But what happens in intensive system is, intensive state variable is the pressure, the temperature, we can't see them, we can't search, we can't find the changes that are going to take place in that system is called as intensive state variable. So this is of two types. The first one is extensive and the second one is intensive, where in extensive we can see the changes that are going to take place. In extensive we can't see the changes that are going to take place in the thermodynamic system. Then comes the equation of state. So what is this equation of state means? The thermodynamic variables like pressure, volume, temperature, so all these things can be connected by using one mathematical relation. That relation or that equation is said as equation of state. So what is that equation means? PV is equals to nRT, where P represents pressure, V represents volume, R represents gas constant, whereas T represents the temperature and N represents the number of molecules that are present in the thermodynamic system. So this equation is stated as equation of state. Next comes is the two definition, or we can say that two phenomena. So which are those two phenomena? The first one is the diathermic wall and the second one is adiabatic wall. So what the definition says here is which allows heat to flow from one system to another system is called as diathermic wall. So if we take one example over here means, wait, I'll insert the shape here. So we have considered the two systems, the first system and the second system. Okay, so here what we have done is we have put an adiabatic wall. Here the wall is diathermic and here the wall is adiabatic. So what happens is the temperature or the heat will move from one system to another system. There is an exchange takes place in diathermic wall, whereas in adiabatic wall there will be a no flow of heat from one system to another system. There will be no flow takes place in adiabatic wall. So the definition says here is the diathermic wall is that wall which allows the heat to flow from a system A to a system B. The heat will flow from system A to system B in diathermic wall, whereas in adiabatic wall the heat will not flow from system A to the system B. This wall can be considered as a boundary here. It will not allow the heat to flow from one place to another place in adiabatic wall. So next one is thermal equilibrium. So what is this thermal equilibrium? States the temperature of the two gases will remain constant. So if we take the two system, this is a system A and this is system B, and here is diathermic wall is present. So what is diathermic wall? As we have discussed now only, diathermic wall is that wall which allows the heat to flow from one system to another system. Here we have taken adiabatic wall. I have written in short form, A means adiabatic, and here also we have considered the two systems, that is system A and the system B. So what happens here is we have taken pressure P1, volume V1 and temperature T1. In system B, pressure P2, volume V2 as well as temperature T2. So in diathermic wall, one condition is given here, that is temperature T1 is greater than temperature T2. So what happens here is higher temperature will move to the lower temperature, that is temperature T1 and temperature T2 will be interchanged, and what happens here is at some point they will attain equilibrium. At some point they will attain an equilibrium, that thermal equilibrium, which means the temperature will remains constant and there will be no flow of heat takes place, that is delta Q will be equals to 0 at some point. So this is nothing but a thermal equilibrium when we have taken an diathermic wall. So here the temperature will remains constant and we can say that it has attained at the equilibrium. Here temperature T1 is equals to temperature T2, which is equals to temperature T. Next we have considered one more case where we have a boundary condition, that is adiabatic wall is present here. So what this adiabatic wall will do, it will not allow the heat to flow from system A to system B, and again we have taken that pressure P1, volume V1 and temperature T1 in system A, and pressure P2, volume V2 and temperature T2 in system B. So can we say that the thermal equilibrium has been attained here? Or we can say that T1 is equals to T2 here. Is that possible? Yes, this is possible. Even though they are having different temperature, this is in equilibrium with the surrounding. This system A is in equilibrium with the surrounding up to where? Up to infinity. Up to infinity, this will be in thermal equilibrium, and here also the system B is in equilibrium and it has attained the equilibrium. So we can say that temperature T1 is equals to temperature T2, even though their temperature is same. Even though temperature is different, still they have attained the thermal equilibrium. Why? Because they both are in thermal equilibrium with the surrounding up to where? Up to infinity. So this is of thermal equilibrium. So I hope this concept is clear for you, and then we will move to the zeroth law of thermodynamics. So in general, if we take like system A, all these, if we keep this aside, if we take some general example like A, B, C, right? So if we take some of the general examples, can we say that this is A, this is B as well as this is C? So hence we can say is both the A and C are friends among each other. That is A and C are friends with each other, while C and B are friends with each other, right? So we can say that A and B, at some point A and B will become friends with each other, right? So A and C are friends, and here C and B are friends. So at some point A and B will also become friends. Is this possible? Yes, this is possible. So this is of general case. If we take example or if we define this, we can say that if two thermodynamic systems are in thermal equilibrium with each other, with the third system, then they are in thermal equilibrium with each other. If we consider this as a system 1 and this as a system 2 and this as a system 3. So if both are in equilibrium with the third system, then they will be in equilibrium with each other. So this is of zeroth law of thermodynamics, where we can say that temperature in T1, that is A temperature, is equals to the temperature which is in C temperature, and here B temperature is equals to C temperature. Then we can say that temperature which is present in A is equals to temperature which is present in the system B. So this introduces the concept of temperature. This zeroth law introduces the concept of temperature. This question can be asked in your exam. So always remember that zeroth law of thermodynamics introduces the concept of temperature. Okay. So next we will move to the internal energy. So what is this internal energy, or how it can be denoted, this internal energy? It can be denoted by capital U. Capital U, internal energy is denoted by capital U, and what it defines is, it is the sum of kinetic energy plus the potential energy. So internal energy is equals to kinetic energy plus potential energy. This is the definition, right? So the thing here we have to understand is the important points to remember in internal energy is that the total energy. So how to write the total energy? Total energy is equals to internal energy plus the external energy, right? Internal energy plus the external energy. Since we are considering the internal energy case, therefore the external case will becomes 0. Therefore this external case will becomes 0. Hence we can say that total energy is equals to internal energy, and now it comes is internal energy is equals to kinetic energy plus potential energy, right? So this is of real case. This is of real case. If we consider the two cases, the first case here is real case, and the second case we will consider here will be ideal case. Ideal case. So in real case what happens is, internal energy is equals to kinetic energy plus potential energy. That is, total energy is equals to internal energy, and internal energy is equals to kinetic energy plus potential energy. But what happens in ideal case? What is kinetic energy here? So kinetic energy can be said that the molecules which are in motion, so they may vibrate, they may rotate, or they may go straightly, right? Or they have some random motion. So they will random motion, they will having some random motion. So this is about the kinetic energy. But what happens the potential energy? This is the intermolecular interaction that is going to happen between the two molecules. The intermolecular interaction which is going to happen between the two molecules is called as potential energy. So in real case, total energy is equals to kinetic energy plus the potential energy. But what happens in ideal case? Ideal case means, if we consider this container will be at rest position. So what is the ideal case? The container which are having some particles, and this container is in a rest position. We can say that the container is in a rest position. Now we will define the internal energy. So internal energy is nothing but total energy is equals to internal energy, and internal energy is equals to kinetic energy plus the potential energy. But what happens in ideal case is, potential energy will turns to be 0, right? So if we consider the molecules will be at rest, then there will be no intermolecular interaction. Then there will be no intermolecular interaction. Hence we can say that intermolecular interaction. Hence we can say that potential energy will be equals to 0. Therefore for ideal case, total energy is equals to internal energy, and internal energy is equals to kinetic energy. Hence we can say that internal energy in case of a ideal case is completely kinetic in nature. So if we solve the examples, one question will definitely arrive. What is the question is? So the internal energy in ideal case is how? So the total energy or the internal energy in the ideal case is always kinetic in nature, is always kinetic in nature, not a potential in nature. Okay, so one more thing we have to remember here is that is, as the internal energy increases, as the internal energy, that is, as U increases, total energy will also increases. As the total energy is increasing, then definitely remember that kinetic energy is also increasing. As kinetic energy is increasing, then definitely remember temperature must and should increase. Okay, so this is about the internal energy. I hope the concept is clear for everyone. Next, we will move to the sign conventions. So, what are these sign conventions? How they are useful? So, these sign conventions are useful while solving the problems that are related to heat, that are related to internal energy, as well as for the work. Okay, the heat absorbed. So, here we will take the positive as well as the negative sign, right? So, what happens if it is positive? The heat will be absorbed. The heat will be absorbed. If the heat is released, then we can say that it is negative. Heat is absorbed, then we will take a positive sign. If heat is released, then we can take a negative sign. So next comes the internal energy. If internal energy increases, means the sign will be positive. If internal energy decreases, means the sign convention will be negative. Okay, next comes is work done. So here work done is done in two process. One is work done by the system, and the second one will be work done on the system. So WD means work done on the system. Many of us will get confused, right? So what is work done by the system, what is work done on the system, how to take the sign conventions. So if we consider the work done by the system, means we are considering a container and there will be some molecules present in this container. Okay, the piston, here is the piston present. So if these molecules they themselves try to expand, if these molecules will expand, then this can be shown as like this. Then this can be shown like this. The piston has been moved from upward. The piston has moved upward, right? So the piston moves upward, which means the container has been expanded, which means we have to take a positive sign. If the container has expanded, that is work done by the system, then there we have to take a positive sign. If it is compressed, then we can say that work is done on the system, there we have to take a negative sign. Okay, I hope the concept is clear in sign conventions. We will move to the work done during the cyclic process. So what happens in work during the cyclic process is, here we will take again the sign convention. If there is a clockwise direction, like this, then we will take positive sign. If there is an anti-clockwise direction, anti-clockwise means we will take a negative sign. If it is like this, then we will take a negative sign. So always remember, in work done, internal energy will always be equals to 0. Internal energy will always be equals to 0. Why? Because if we consider this as a cycle, if we are considering the clockwise cycle, right? We are considering here the clockwise cycle, A, B, C as well as D. We have taken A, B, C, D, and what happens here is, in this cyclic process, area will be equals to A, B, C, D, A. Here the initial as well as the final positions are same. Hence we can say that work done during a cyclic process, the internal energy will always be equals to 0. Always remember this thing. Okay. So next thing we will move to is area under PV diagram, which gives us the work done. So what is this PV? P means pressure and V means volume. If we plot the graph of pressure versus volume, we will get the work done. Okay, so how it is done? We have to take the area that is under this PV curve. So look at here, I am drawing that the area is under the PV curve. Okay, so this area we will consider for the PV diagram. So this thing we have to solve this in an example. There we will get the idea of area under PV diagram, how the work is done in this process. Okay, so next one here we will discuss is first law of thermodynamics. So last concept of our today's class. So what is this first law of thermodynamics says is delta Q. Delta Q is equals to delta U plus delta W. So what is delta Q here? The heat supplied. What is delta U here? Internal energy. What is W here? That is the work done. Work done during the process. So how it can be said that delta Q is equals to delta U plus delta W? If we consider one simple example or simple thing we will discuss over here is, if we consider this container and some of the particles are present over here, and if we supply the heat energy, we are supplying the heat energy to this system. So if we supply the heat energy means delta Q is supplied, right? So the delta Q is supplied and delta Q is given the work, that is delta Q is converted into delta U plus delta W. So how it is converted? The heat is supplied. If heat is supplied means internal molecules will expand, right? Internal molecules will expand, that is internal energy is produced. The kinetic energy is produced. If kinetic energy increases means internal energy increases. Here the temperature increases. So you can say that delta W is formed here. Then the work is done. If these molecules will try to expand from this to this. So they have expanded. So there will be a slightly expansion takes place, and that expansion is nothing but the particles have done the work. The particles have done the work, right? So the heat is supplied to the system, which is converted to delta U plus delta W, that is delta Q is equals to the heat supplied, which is converted to the internal energy as well as it is given to the work done by the system. So this concept or this first law of thermodynamics introduces the concept of internal energy. And always remember, first law of thermodynamics is conservation of energy. First law of thermodynamics will always says the conservation of energy. How it says? That energy is neither be created nor be destroyed, but it can be transferred from one system to another system, right? The same thing has been happened over here, that is delta Q. This delta Q has been transferred to delta U plus delta W. So we can say that the first law of thermodynamics is concerned with the conservation of energy, where energy can neither be created nor be destroyed. Here the heat energy is neither be created and it nor be destroyed, but it is transferred from where to where? It is transferred from internal energy to work done. So this is of first law of thermodynamics. So now we will move to the I hope everyone has got their concept clear. So based on these concepts we will solve the previous year questions, so which are appeared in NEET, JEE, CBSE as well as in NCERT session. So what is the nature of the internal energy of an ideal gas? We have discussed it, right? So in ideal case what happens is total energy is always equals to internal energy, and internal energy is nothing but kinetic energy plus the potential energy. But in ideal case the container will be in a rest position, hence there will be no intermolecular interaction takes place, therefore potential energy will turns to be zero. Hence the nature of the internal energy is purely kinetic in nature, purely kinetic, right? So I hope the first question is clear for everyone. And next question is, in which among the three processes shown in the given figure work done is maximum? So this is, one is the initial position, two is the final position. So this first person went from school to home. So he has taken the three routes, right? So this is the first route, this is the route A, this is the route B, and this is the route C. So three routes he has taken, and where the work done is maximum. They have asked the question is where the work done is maximum. So here we can say that the work done is positive, since this is cyclic process, therefore we can say that it is in a positive direction, therefore it is a positive. The first thing is clear, the sign convention is clear. And all the three processes, since gas expansion is going from 1 to 2, this person is going from here to school to home, that is he is expanding, so therefore it is of positive sign. And work done is equals to, always remember, work done is equals to area under PV curve. Area, as we have discussed, work done is equals to area under PV curve. Area under PV curve. So what is the PV curve here? This will be the PV curve, right? So what is the work done here? For the C, only this much of work is done. For B, this much of work is done, right? For B, only this much of work is done. But for A, the work done is this much. So hence we can say that work done is maximum in A as compared to B and C. So work done in A system or in A is maximum. Okay, I hope the second question is clear for everyone. So the third question here is, an ideal monoatomic gas is taken round the cycle ABCD as shown in the given PV diagram. So here one thing, remember, the sign convention is positive or negative, since this is in a clockwise, right? So this is in a clockwise direction. So hence we can say that the work done or the sign convention will appear to be positive. Why? Because it is of in a clockwise direction, right? So what we have to find is, find the heat absorbed by the gas in this process. So we have to find here is delta Q. We have to find here will be delta Q. So work done in the cyclic process is area of the cycle. So what is the area of the cycle is? Up to, in pressure, this is up to the area of cycle, and here will be, it will be up to this much, right? So this much. So area under PV curve, that is work done is equals to area under PV curve. PV curve, that is 4P minus 2P and 2V minus V, which gives us 2PV, right? So this is W, this is W. 2PV is nothing but our work done, right? So next what we have to find here is, we have to find the delta Q. So how to find this delta Q? By our first law of thermodynamics. So first law of thermodynamics. So what is this first law? Says that delta Q is equals to delta U plus delta W. So for a cyclic process, one thing we have remembered here is, for a cyclic process, always remember what I said, delta U is always equals to 0, that is internal energy is always equals to 0, hence delta Q is equals to delta W. And what is the value of delta W? It is, we have given here, right, that is 2 PV. 2 PV, that is the heat absorbed by the gas in this process, that is delta Q is equals to 2 PV. I hope the third question is clear for everyone. Then the fourth question is, the first law of thermodynamics is concerned with the law of conservation of, right, energy. That energy can neither be created nor be destroyed. In the same form, it is transferred from one system to the another system. So the first law is concerned with the law of conservation of energy. Next is, an ideal gas undergoes cyclic process. So this is going a cyclic process. One thing here is, it is in a anti-clockwise direction, right? So here if it is in anti-clockwise direction, then the work done will always be in a negative. That is, the answer here comes will be negative. So if we check the examples, or if we check the option, the only thing that is negative here will be minus 2V, right? So by using our common sense, we can solve this in a few seconds, right? So the work done here will be in anti-clockwise direction, so it is negative, hence the only thing here negative value is in these options is option B, that is minus 2 P naught V naught. So if we check it by the example, so how we can say that? Area under PV curve, right? So this is area under PV curve. Work done is equals to area under PV curve. So what is area, or the work done here will be 2 P naught, and here it will be 3 V naught minus V naught, that is 2 P naught minus P naught and 3 V naught minus V naught. Here we will get is P, and here we will get is 2, that is 2 P naught V naught. Since this is of anti-clockwise direction, therefore we have taken a negative sign over here. So work done will be minus 2 P naught and V naught. Fifth question is clear. Okay, we will move to the last question of this session, that is, an ideal gas expands along the path AB as shown in the given figure. So this is going along this direction. This AB is going along this direction. Calculate the work done. Here we have to find the work done. That is, work done is equals to area of. So as this looks like a trapezium, right? So this looks like a trapezium. That is, work done is equals to area of trapezium, that is ABCD. And what is the formula for it? Area of trapezium is equals to half into sum of the parallel sides, into the distance between the parallel sides. So if we put the values, we will get half into, that is here we will take 8 minus 4, that is 4 plus, and here 0.4 minus 0.3, it will be again 0.2. So 4 plus 8 and into 10 to the power minus 5 into 10 to the power, this is 10 to the power plus 5 into 0.5 minus 0.3 is 0.2, which is equals to, so after solving it, we will get 12 into 10 to the power 4. Since this is in joule, work done will be in joule. So I hope the concept is clear for everyone. So in the next session we will move to the another topic of this concept only, that is specific heat capacity, thermodynamic process, as well as the second law of thermodynamics. So thank you everyone.